Hello everyone and welcome back to the final vodcast on covalent bonds by Mr. Mahan. This final vodcast is going to first review that idea of polar bonds, and then it's going to get into how that relates to polar molecules and what this idea of polar or nonpolar molecules is all about. So to start us off, if you remember in our last vodcast and in one of our last lessons in class, we said that based on the difference in electronegativity in a covalent bond, we can classify it either as nonpolar, which means a complete even sharing of the electrons, a polar covalent, which means that we are still sharing but it's uneven, or a full ionic bond where it is no longer a covalent bond, there is an actual give and take or transfer of electrons. We took that information and we said that we will point to the negative or the stronger atom, and therefore we will have a partial negative charge, a partial positive charge, and we have this idea of opposite charges. To get you guys going and get you familiarized with the idea of what does it mean to have a pole, I reminded you guys that we have this thing called the North Pole and the South Pole on Earth, and sometimes the geological or the geographical North Pole is not necessarily the magnetic North Pole. But we review the idea that you don't need to be right on the North Pole or the South Pole for that matter in order for a compass to work. That a compass will work in Farmingdale, New Jersey, California, Mexico, South America, Africa, in the middle of the Safari, in the middle of the Atlantic, in Canada, all over the world. Compasses work because even though the pole are at the extreme north and the extreme south of the world, we have this field, we have this interference, we have this area in which we can still feel that pole, that charge, that magnetic interference, if you will. I related that over to one of maybe possibly your childhood toys that involved the iron fillings, and if you look at this bar magnet that's been placed upon a bunch of iron fillings, you can see specifically that these iron filings are, even though they're not necessarily right next to the pole there, we are still actually interfered with, or we still feel the influence of those poles because that field that the pole gives off encompasses more than just the area where the pole is located. And that's very important because when we start to look at molecules, and if we were to look at these graphics here, when we start to look at molecules, we only consider a molecule polar if it has what we call poles, if it has a positive side and negative side. If I come in from one side here, if I come in from the top, you could see that I would see a positive charge in this blue compound, and if I come in from the bottom, I would see a negative charge. And therefore, since I see opposite charges, this is a polar molecule or a polar substance because it has the opposite charges. Here I would see a positive charge, here I'd see a negative charge. Again, I am polar. Now, just because you have charges does not mean that you are a polar substance. You need to have that ability to come in from one side and see one charge and come in from the other side and see an opposite charge. And you do not have that in these examples over here under the no pole section. And if you take a look, if you come in from this angle, yes, we do in fact have a negative charge. And if you were to come in from the bottom, again, you would see that you also have a negative charge. But what isn't quite apparent right away is the fact that even though, yes, there is a positive charge in the middle, you can never get to this positive charge here because just like the Earth, just like those bar magnets, these negative charges, these negative poles have fields. They have like force fields that are being given off that protect and insulate and do not allow a particle or anything to see or get into that negative. So we have these force fields that are being given off by these poles that actually in fact overlap. I'm sorry you can't see this. Maybe I should not have used this red color. I thought the red would be a good idea. But these force fields are being given off by these negatives, and they're overlapping, and they are not allowing us. They are not allowing us to get into that positive center. Again, the force fields would look something like this. So, although you may think that you can get to that positive charge, you cannot because of these force fields. So every single way that I attack this molecule, every single direction that I come in, I see nothing but a negative charge. And so since I do not have that positive on one side, negative on the other side idea going on here, we say that it is not polar or that it does not have poles. Now, just like in our previous vodcast, we defined a polar bond as a bond that has one side of the bond slightly negative. In this case, it would be the fluorine side that is slightly negative, the oxygen side that is slightly positive. Well, in order to be a polar molecule, you must have one side of the molecule that is slightly positive and one side of the molecule that is slightly negative. And the most popular, most well-known polar molecule in the scientific community is dihydrogen monoxide, aka water. And if you take a look at water here, as I come in from the oxygen side, if I come in for an attack or for a landing here from the oxygen side, you're going to see that you see all negative charges. But if you come in from the hydrogen side of the bent molecule, you're going to see positive charges. And so because I have a positive on one side, a negative on the other side, we say that water is in fact polar, and I proved it to some of the classes in class using that charged pen trick. Now, in order to be a polar molecule, you have to have a couple of things going your way. First off and foremost, to be a polar molecule, you must have polar bonds. If you are going to have a charge on one side of the element and a charge on, on one charge, in order to be a polar molecule, you must have two things. First off and foremost, you must have polar bonds. If you're going to have a positive charge on one side of the molecule and a negative charge on the other side, well, you have to have polar bonds to give you those charges. Now, it's not just good enough to have polar bonds. In fact, you must also have a polar shape. And the way that you could think of about, do I have a polar shape, is if you look here, if we were to look and break down our molecules, if you can draw a line through the molecule anywhere and separate it so that coming in one side I see one charge and coming in the other side I see an opposite charge, I am polar. Again, I separate the molecule, I come in this way, I see one charge, come in this way, I see another charge, I am polar. Separate the molecule, positive on one side, negative on the other, I am polar. Now, this is not limited to strictly the trigonal, pyramidal, linear, or the bent shapes that you see here. This could also affect a trigonal, planar, and a tetrahedral shape as well, because once again, if I separate this molecule and look from one side, I see a positive, the other side a negative, one side a positive, the other side a negative. So not only do you need those polar bonds, but more importantly, you must also have a polar shape in order to be a polar molecule. Now, nonpolar molecules are even trickier because nonpolar molecules may have polar bonds. Whoa! So just because you have polar bonds does not mean that you are a polar molecule. Problem here is if you have the quote-unquote wrong shape, you will not be a polar molecule. And what I mean is if you take a look at these examples here, we have a trigonal planar. Now, because this is surrounded by negatives on the outside, if I come in from this side I see a negative, this side I see a negative, this side I see a negative. And again, you may say, "Ooh, Mr. Rahan, I am part ninja. I can sneak in and get to that middle atom." But you have forgotten that these negatively charged species, these negatively charged atoms, are giving off little force fields. And these little force fields actually completely overlap. And so on your way in, you would see a negative charge, and if you were a positive thing, you would be attracted to the negative charge, or if you were a negative thing, you would be repelled by that negative charge. Same thing here with this tetrahedral. Since I'm completely surrounded by negatives, I have nothing but a bunch of negative force fields surrounding, protecting, and insulating my positive center. Here with this linear, again, these positives are going to insulate this negative with their positive force fields and is not going to allow you to ever get to that negative middle. So if you have polar bonds, you can still be a non-polar molecule by having the quote-unquote wrong shape. Last way that you can actually be a non-polar molecule, simplest way of all time, well, if you do not have at least one polar bond, if you are completely constructed of nonpolar bonds so that you have no charges whatsoever in your atoms, you are going to be a nonpolar molecule. Okay, so if we take a look at a little bit more of a practical application of this idea of polar, nonpolar molecule, well, if we go back to this worksheet that we were working on earlier in our polar, nonpolar vodcast and the worksheet that we had for homework, we should have already had sulfur dioxide drawn. We see that it is a bent shape. And since my electronegativity difference is 0.1, I actually end up with an NPC, a nonpolar covalent bond that occurs between the sulfur and the iodide. So because it's an NPC bond, I do not need any arrows, and because I do not have one polar bond in my entire molecule, that means, therefore, that my molecule must be an NPM, a non-polar molecule. Okay? Now, if you look at this next one, the tetrahedral of carbon tetrahydride, I actually do have polar covalent bonds now with a electronegativity difference of a 1.5, but because every single arrow is going to be facing out towards the fluorine, which is stronger, I actually have like a negative all the way around. So no matter which way I try and approach this element, this molecule, no matter which way I try and come in, no matter which way I take a look at it, even though it's filled with polar covalent bonds, because every way that I look at it is going to end up showing me a negative charge, and I will not be able to get through their force fields to get into that positive center, this too is a non-polar molecule, even though it has polar bonds because it has the quote-unquote wrong shape. Now, carbon tribromide, carbon trihydride monobromide, this was an evil question, because we actually had two types of bonding going on here. We had a carbon to hydrogen bond and a carbon and bromine bond. And the carbon to hydrogen bond is 0.3 difference in electronegativity, so that's an NPC, that's a nonpolar covalent bond. But the carbon to bromine bond is 0.5, and that's a PC. And so that's why I end up with only one single arrow here, because I only have one carbon to bromine bond. Now, with what that's showing me is that as I come into the molecule this way, I'm actually going to see a negative charge because bromine is stronger than carbon and is going to be holding on to those electrons more. What that also tells me is because these other bonds are nonpolar covalents, they are not protecting this now slightly positive side like they were in the above example. And so if I were to come in this way, I'm going to see a positive charge. And therefore, since I have a negative side on one side, a positive side on the other, I now do have a polar molecule. So remember, when discussing is it a polar or nonpolar molecule, the first question to ask yourself is, do I have a polar covalent bond? As long as I have at least one polar covalent bond, I may be a polar molecule. I then have to go back to my shape and my Lewis dot structure, analyze the shape and see, can I see a positive and a negative like I do in this example, or am I surrounded by one charge like I am in this example? If I see a positive and a negative, I'm a polar molecule. If I'm surrounded by one charge, I'm a nonpolar molecule. If I do not have any polar bonds in me at all, there's no chance of my molecule being polar. I hope this vodcast has helped you further understand the difference between a polar bond and a polar molecule, and understand exactly how to say, aha, this molecule is polar or is not polar. Thank you for watching, and have a great night.